Hello, my name is Vojtěch Čermák and I am here to introduce SeaTurtleID, a long-span dataset for reliable sea turtle re-identification. In my presentation, I will first discuss our motivation, introduce the dataset, and finally showcase why timestamps are essential for animal re-identification datasets. Our work focuses on wildlife re-identification, which is not about species identification, but recognition of individuals within one species, in our case, caretta caretta. Like other species, turtles can be visually identified based on stable features, for example head skews, that do not change throughout their lives, even though there is considerable change in coloration and pigmentation and some scratches might occur. For the sake of example, we recognize a change in appearance for two individuals. While the coloration might change, the shape of head skews remains the same even after 7 years. Even though automatic wildlife identification might significantly impact the study of many aspects of wildlife, such as population or migration studies, there are several problems with dataset collection and curation. First, datasets are usually split randomly, which often results in performance inflation due to training to test data leakage and background overfitting. Second, the span of the data is short, usually within 1 or few days. Therefore, there is just a minimal change in the capturing condition, the environment, and the lighting conditions. If you look at the images, you can spot at first glance that the matching is much easier within the same day. Learning from that, we introduced the SeaTurtleID dataset. The dataset consists of nearly 9,000 images of over 400 individuals collected within 13 years, making it the longest span dataset for animal re-identification. All photographs include various annotations, for example identity, encounter timestamp, and body parts segmentation masks. Instead of standard random splits, the dataset allows for two realistic and ecologically motivated splits, a time-aware closed set with training, validation, and test data from different days and years, and time-aware open set with new unknown individuals in test and validation sets. To establish the baseline performance, we studied local descriptors such as shift and superpoint and deep metric learning approaches such as arcface and triplet. For the metric learning, we used swim-based architecture as the backbone, extracted features, and used k-nearest neighbor matching for the prediction. In general, we can say that metric learning outperformed the local descriptors by a large margin. Additionally, the arcface showed more stable performance than the triplet loss. For instance segmentation, we compare mask-to-former, HTC, and mask-RCNN methods. Overall, the mask-to-former performed best. However, the HTC model excelled in the head segmentation, which is crucial for re-identification. Besides the benchmark, we have prepared a straightforward approach for turtle re-identification. During development, we studied how each body part contributes to performance and found out that matching just heads yields the best results. Maybe surprisingly, using flippers, which also have unique patterns, did not help. Besides, we explored how to take advantage of a timestamp in production. We significantly improved performance by grouping images from the same individual using the timestamp. In our case, we reduced the relative error by approximately 40%. Last but not least, we provide qualitative evidence to prove the importance of time-aware splitting. We trained two models. First, train data split randomly, and second, using the time-aware split. Below, you can see the GradCam visualization that showcases how background pixels are used for identification if data are split randomly. To provide additional evidence for the hypothesis that there is training to test data leakage and models trained on random split learns to recognize identities primarily based on the background, we experimented with training using just background and foreground separately. As expected, models trained using a time-aware split significantly dropped in performance. Contrary, models trained using random split maintained high performance. That's all. Thank you for your attention. If you are interested, you can download the dataset here.